Okay, this is section 3.2. It's investigating quadratic functions in standard form. And in 3.1, we looked at vertex form. And so just writing it right here, vertex form is a times x minus p in brackets squared plus q. And that's a really useful form of the equation. You have a that tells you whether it opens up or down and how wide or narrow it is. And you have p and q that are the coordinates of the vertex. Okay, and so if you write out your equation in standard form, you still have the a value. The a values are the same, but you have b and c. And b doesn't have a lot of real useful, or it's not a really significant. C is quite useful because it is your y-intercept, right? When you put in 0 for x, those first two terms go away, and you end up with y equals c. Okay, so they both have different characteristics that make them useful. All right, so in this activity, it asks you to model the path of a football. So we draw a coordinate grid, just an x and y axis. Okay, x-axis is horizontal distance downfield, and y is height. And we're just going to draw some possible paths of a football. Okay, so just like in the diagram, or the picture that they have down there, you have the punter kicking the football, and he starts at a height that's not 0 because he kicks it a little bit in the air. Okay, and so here are 3 possible flight paths. You could have a high and short kick, or sort of a medium kick, or a long, low kick. Those are all possible shapes. And so to describe the shape of your graphs, or what they have in common, well, they all kind of go up and then they come down. Okay, and that's called a parabola. We learned that in the last section. So what do they have in common? They all have, they're all symmetrical. Okay. Each of them has an axis of symmetry, and that's a vertical line that goes in and cuts it in half. Okay, and obviously I didn't draw the perfect parabola here, or that would look more symmetrical. I think the first two are better than the last one. Okay, but they each have an axis of symmetry, and all of these have a maximum value. Okay, so if you describe the maximum or minimum height of each of your graphs, you have a maximum height because it's a parabola opening down. And the minimum height here, you wouldn't have it if it was just a mathematical graph of a parabola, but because this is a real world example, you're going to have a minimum height of 0. Obviously, it's not going to go down below the field. So in this specific case, you have a domain that's from 0, okay, to the end of the horizontal distance that the ball travels, and you have a range from 0 to the maximum height that the ball reaches. All right, so in part B, we're just going to do some different things, and we're going to investigate how the values of A, B, and C change the graph. The path of a football through the air is just one of many real-life phenomena that can be represented by a quadratic function. And when it's written in the form ax squared plus bx plus c, that's standard form. Okay, so a little different than vertex form. We're going to start by graphing the function f of x equals negative x squared plus 4x plus 5. All right, and in 3.1 in the lesson, or I guess in the notes, I gave you the link for this. This is the graphing calculator that I use online. And just put those equations in, and we just graph it, okay? And so you can see describe any symmetry that the graph has, and does it have a maximum y value and a minimum y value? Well, the symmetry is that the line x equals 2 is the axis of symmetry, and on either sides of the line you have a half of the graph and they're mirror images of each other. Okay, it does have a maximum value. That maximum value is 9. Okay, and the minimum, there's no minimum. It'll keep going down forever. And what I wrote on the side there on that table, you can see that it goes from 8 to 9 to 8 as the x value is 1, 2, and 3. So you know that that 9 is the maximum value, and the x coordinate that goes along with that is 2. Okay, so the coordinates of the vertex are 2 and 9. Okay, and you can't really get that from the equation like you could if it was in vertex form. Okay. Yeah, I get zoomed out there just to show you that it just continues going on forever in the negative direction, the y value, right? Okay, so it doesn't have a minimum y value. So let's try um, a few different functions. Okay, we're going to have the first two terms the same. The only thing we're going to vary here is c. So we're going to take negative x squared plus 4x plus 10, and then plus 0. And I missed what that other one was. All right, so just inputting those, c equals 10 in the first one, c equals 0 in the second one, and c equals negative 5 in the third one. Okay, we'll just see what happens when we change that. Okay, and so what you should see, we'll zoom in so we can get a good look at it. It's the same shape of graph, and all that happens is that you're moving it up or down. Okay, so what it changes there is the y-intercept, which, as I mentioned, you get when you have an x value of 0. Okay, those first two terms are the same. Notice the vertex doesn't change. It doesn't shift to the right or the left. All it does is shift up or down. And you can also see that the green one goes through the origin because its y-intercept is 0. Okay, so we're going to look next at what happens when you change the a value. Okay, we'll have an a value of negative 4, negative 2. I think that was 1 and 2. Okay, so just taking the same function, same values of b and c, and substituting a different a value in. All right, and you can see what happens to our graph. I just have to hit the graph button here so it changes them. Okay, one thing you might notice is that the ones with a larger, the larger the a value, whether it's positive or negative, I guess the greater the absolute value of the a value, the narrower it is. Okay, the narrowest one is the red one with an a value of negative 4. It opens down, that's where the negative comes in. You might notice that the green one and the yellow one have the same width, basically, although one opens up and one opens down, and the blue one's kind of a normal width. And also notice how the vertex shifts. It does shift both vertically and horizontally when you change the a value. Okay, and that's kind of a characteristic of the standard form equation. You wouldn't see that in a vertex form if you didn't change p and q and you just changed a. Okay, so we'll get to that in our summary. And then finally, we'll look at what happens when we change the b value. All right, notice the second one, that green one, doesn't actually have a b value, all right? That's okay. Remember, the x squared term is mandatory and all the other ones are not. Okay, notice changing the b doesn't change the width at all, okay? But what it does do is it shifts the vertex. Okay, so the vertex will be shifted vertically and horizontally by changing only the b. Okay. All right, so what does that show you about how the function is affected by changing the parameter c? We saw a vertical shift. When you change a, it's going to widen or become more narrow. Okay, and just to show you how the sorry, I'll go back to that y-intercept. When you have it in standard form, if x is equal to 0, remember when you found a y-intercept with lines, you set x equal to 0 to find out what y is. Okay, you do that here. Your first two terms are both going to become 0, and you're left with c. Okay, that's why c is your y-intercept. All right, how does it change when the value of a is changed? Well, we know that it changes whether it's up or down. Okay, when a is a positive number, it opens up. When it's negative, it opens down, and a affects the width, and a will also shift the position of the vertex. So it doesn't say that in your book, but it's pretty obvious. We did it. We could see that a shifted the position of the vertex. Okay, and then changing the value of b, we saw that that was a shift. Okay. All right, so let's drag up this link the ideas and see. This is what it says in your book. Okay. That a determines the shape and whether the graph opens upward or downward. B influences the position of the graph, and C determines the y-intercept of the graph, which is also position, right? That's vertical position. Okay, they don't say that A influences the position, but we could see that it did. Okay, and when we look at how you can calculate P and Q, you're going to see that A is part of that calculation. We'll just see that in a second. Okay. Notice here, it just shows you how you can take a vertex form equation and turn it into a standard form equation. Okay, so if you look, f of x is equal to a times x minus p squared plus q. Okay, what we do is we can square that binomial, x minus p, and what you end up with is that trinomial that's in the brackets there. Okay, x squared minus 2xp plus p squared. Okay, the next line, they just distributed the a through there. Okay. So got rid of the brackets. And then in the fourth line, you took the x squared part, you took the x part and its coefficients in brackets, and then the constant part, that's just the part that doesn't have any x. And then this is not a continuation of that. They've just put the standard form there to compare it. You can see that the x squared terms are the same. B is in front of the x in the second one, and it's negative 2ap in the first. So that's where they get this whole idea that b is equal to negative 2ap, or you can find p by going negative b over 2a. Okay, and the same thing with that last part. That's equal to c. Okay, so that just is where they get these two. Okay, b equals negative 2ap. Okay, or you can solve that for p. And then the next part, c equals ap squared plus q, or q equals c minus ap squared. Okay, and so you can see that actually a does influence both p and q. Okay, and b influences them both too, because b influences p, and then p is part of the calculation of q here. Okay, so those are two things that you can memorize, but you don't really have to, because we're going to learn a better method than that in the next section.